All right, this is part 2 for the OFI testing equipment permeability plugging tester. In part 1, we covered the initial setup, we covered the pressurization using the hydraulic pump, we covered how you hook up the inlet manifold assembly, and we also covered the heat expansion for the fluid, where we allow the heat expansion to go downward. The hydraulic fluid goes back into the pump, if you will, instead of the common mistake a lot of people make with a high temperature, high pressure filter press. They leave an 1.5 inch of void space at the top of the cell for the heat expansion. These ceramic discs have to be soaked, have to be pre-soaked, at least for an hour, preferably overnight, if not perpetually, in the base fluid that you're using, whether that base fluid is water-based fluid, diesel oil, or synthetic oil for oil-based fluids or whatever. But the soaking enables you to get better flow channels through the ceramic disc. If you put a dry disc in there and you hit it with particles, those particles are going to unusually seal up that disc, so you collect a lot less filtrate than you normally should or would. So that's the reason for pre-soaking these discs. If you leave an air pocket beneath your pre-soaked disc, as soon as you hit your cell with pressure, that air pocket is going to void out the pre-soaked disc. So for that reason, we fill the cell all the way up to the O-ring lip, and then we put the ceramic disc literally on top of the fluid. We leave no space between the fluid and the ceramic filter. And if there's any heat expansion that takes place, the piston is 1.5 inches above the inlet cell cap. The heat expansion will drive the hydraulic fluid back into the pump. So the first thing we're going to do is we're going to fill the cell very carefully with our test fluid. This is a polymer-based fluid that we mixed here in the lab. This is not a field mud. This is a laboratory polymer fluid. And we're going to pour this into the cell very carefully, pouring it down the center of the cell, being careful not to get any on the O-ring seal or the O-ring lip. I'll try to do this without getting in the way of the video. I feel it almost perfect. So that is just below the lip of the O-ring. I want to check, make sure I don't have anything interfering with my O-ring seal. The next thing I want to do is I will take one of my pre-soaked discs. This is probably a 60 micron disc, something like that. So we should collect a fairly good amount of filtrate. I want to carefully place this in the cell and push it down so that it comes in contact with the O-ring seal. So now we're ready to add the cell cap. I found that I have the cell cap, I have the outlet ball valve, pressuring outlet ball valve assembly, and this helps to attach the cell cap. I'm just using this as a convenience. You want to initially push, initially you want to make sure that you have greased your O-ring seal, which I've already done, but I will demonstrate again. Put just a small amount of grease around your O-ring. The reason for that is that the heat and temperature is going to expand everything, the metal, everything. So it's very difficult to get these cell caps out of the cell in some cases. So one of the best things you can do for yourself is to put a little grease around the O-ring. It doesn't interfere with the seal. Then when you put it in, you want to push it straight down. You want to make sure that you're not cross-threading anything. And then you can use the outlet valve assembly as a means of starting the cap, which literally, for the 4,000 psi cells that we have, they literally just screw into the cell body. And it works fairly well to a point until it almost gets tight. Then you have to use the strap wrench and the spanner wrench in order to complete the seal. So we do this thusly. We put the spanner wrench around like so. We tighten it down. That acts as an anchor. And then the spanner wrench has a couple of knobs here that fit in the holes on the cell cap. And this groove goes around the valve stem. So now we can tighten thusly, using the strap wrench to anchor the cell in place. So we want to get a good, firm, tight seal, and that's pretty darn tight right there. So now we have the cell and the cell cap in place. We're preheating. Right now we're up to about 230 degrees. So we're above the boiling point of our base phase water. And that is reading at a little over 3. I'm going to set it at 3 and see what that is. These thermostat numbers, the thermostats that we sell on all of our high temp filter press, they're rated numbered 1 through 10. That's not a temperature. It's up to the individual laboratory and or person to mark each of these numbers, what that corresponding temperature is. So if number 3 is 230 degrees, I would take a mark slot pen and write 230F on it. So that each temperature for each number, and they vary. So you have to do that yourself with your own particular high temp filter press. One thing that the API says to do is to take a syringe, fill it with water, and measure the amount of void dead space in your outlet ball valve assembly. You can do that if you want. I found it's usually a fraction of a millimeter. It's really not worth fiddling with, but nevertheless, that's what the API calls for. So it's up to you if you want to do it. This valve stem has been tightened all the way as tight as I can get it. These valve stems are set so that when you do tighten them down, it seals off the cell. It does not allow anything to come in through the valve stem or come out of the cell through the valve stem. So I want to tighten that all the way, which I have done. Then I want to loosen it about a quarter of a turn. You see a little pressure came out of there because it's heating up. I'm already collecting filtrate. This is the heat expansion that I was talking about a minute ago. The heat expansion due to the temperature. So we have allowed, now we've opened the cell so that pressure can get in and out of it. I want to close this ball valve, however, to prevent any more of that from happening. This ball valve, whenever it turn it around to show you. This is open. This allows fluid and pressure, air pressure to pass by. If I turn it 90 degrees parallel to this, that seals the system off. So that's just the way these things work. So that's tight, so I'm going to loosen it a quarter of a turn. The cell is sealed because the ball valve is sealing it. Next thing I want to do is I want to pull the cell rest plunger pin out so that I can lower the cell into the heating jacket. So now I'm getting a better heat transfer from the heating jacket to the cell, and consequently, hopefully, from the cell wall into the fluid. The next thing I want to do is there's a pin, there's a cell rest stop pin in the bottom of the heating jacket. That pin will prevent the cell from rotating inside the jacket. That, once it falls in that place, then I can turn the I can turn this without the cell moving I can tighten things, I can loosen things, and the cell stays in place. So what I do is I use the outlet assembly, I turn the cell until it falls in place, and you'll see and hear it there. Now the cell is in place. I'll loosen it again a quarter of a turn because that's the position that I want it to be in. And now we're heating. I want to take my dial thermometer from the heating jacket and I want to put it in my cell. So now we're getting a closer reading of what the fluid temperature is. Here we're reading the heating jacket temperature, and it's going to be hot because the heaters are down here. I've taken it out and I've put it in the cell, and now the temperature has fallen. It was about 230. Now it's indicating a temperature of about 170. That's because the cell hasn't been subjected to the heating jacket long enough to heat up. So the next thing I want to do now is assemble my back pressure receiver and the CO2 pressuring assemblies. Back pressure receiver is this device here. It is a 100 mil receiver. I'm using it in an upside down position. Normally, conventional high temp filtration testing, this taper on the bottom is the outlet side of the receiver. This is the inlet side. But since we're using this in a reverse position, I'm going to use the back pressure receiver upside down. One thing that you can do with this type of filtration testing, this is the 500 mil heating jacket, a standard 500 mil filter press cell. If you want to use it conventionally as an HTHP, or if you want to use it as a permeability plugging tester, you can buy an extra 100 mil back pressure receiver so you can use it conventionally, and that way you don't have to remove valve stems and bleeder valves and use pipe thread dope and stuff like that. Just get an extra receiver and you can use this device both ways, as an HTHP filter press or as a PPT. So I'm going to attach this with with a lanyard, retainer pin and lanyard on the valve stem, making sure that my O-ring is in place and is in good order, and it is. If I look through here, line the grooves up, voila. And then I want to apply my cotter pin on the opposite side with a lanyard. That way my retainer pin cannot possibly come out. The next thing I want to do is I want to attach my CO2 pressuring assembly. I want to make sure this is tight, by the way. If this is all the way turned clockwise, then this outlet valve is closed. So the next thing I want to do is attach the back pressure receiver. Invariably, sometimes these CO2 bulbs will have pressure in them. These CO2 bulbs, by the way, have between 900 and 1,000 psi. People don't realize that they contain those kinds of pressures, but they do. So it's always good to start off with a new CO2 bulb. You can sometimes run multiple tests with a bulb, but it's good to run if you start off with a CO2 bulb. And this one had pressure in it. It's not harmful. It scares people sometimes, but it's not harmful. So what I'm going to do, put my CO2 bulb in the barrel, and then just start it but not puncture it. I want to attach this to my inlet valve on the back pressure receiver. And again, lining up the holes thusly. So now I have my, if I can make the thing stay, now I have my receiver attached with the lanyard. So it's not coming off. It is not going anywhere. So we've got our fluid is cooking. It is heating up to temperature. whatever that is. As I said, I'm not really too concerned with temperature. This is just for demonstration purposes. I'm not even concerned with pressure for that matter, but we'll pressurize it up to about 1,000 psi, something like that. I'm going to put about 100 psi on the back pressure receiver so as not to evaporate my filtrate. I'm elevating the boiling point of my fluids. So we've got the 100 mil back pressure receiver. This valve is closed. We have back pressure receiver here. I want to make sure this valve is closed, and it is. I want to make sure that this is backed off all the way so that when I puncture this, I won't be depositing the full CO2 bulb pressure into the receiver body. So the next thing I want to do is puncture the CO2 bulb and start the pressurization. So I tighten this down, not overly much, just until it gets tight, and then a little bit. And to add the pressure to it, I turn my regulator T-screw. And that is about 100 psi right there, as read by the gauge. So what we've done now, we have pressure going into the regulator from the CO2 bulb. I have opened the regulator. By tightening this T-screw, I'm depressing a diaphragm, a flat rubber diaphragm, which allows the pressure to go past the inlet side to the side and into the back pressure receiver. So now I have 100 psi down to here, down to the ball valve. This ball valve is preventing me from putting pressure into the cell, because I don't want, at this point, pressure to come into the cell from the back pressure side. I want pressure to come in from the inlet side. And what I do is basically whatever my chart says the back pressure needs to be, that's what I want to put on the inlet side. The chart that we have, that I'm going by, is this right here. If we can see that, it's having a hard time focusing there. But with all of the instructions that OFI gives you, if it's the low pressure, if it's the or the low volume, the 175 mil high temp filter press or the 500 mil high temp filter press, we give you a chart very similar to this, and this will tell you in this temperature range, this is the back pressure you want. This back pressure will be above the vapor pressure of the fluid, and that assures you that you will not end up with steam if you're going above the boiling point of your liquid. So in this case, we're going to be in the 200 to 300 temperature range, 200 to 300 Fahrenheit temperature range. So I'm going to be somewhere around 100 psi. So that basically is what I'm doing here. The inlet valve stem is loose, it's open. So whenever I open this valve thusly, and I apply pressure with a pump, I am putting pressure directly into the cell. So I'm going to start doing that. It will jump up, and well, I've got good pressure. I've got good pressure already. So I'm going to try and lower. You can regulate your pressure with, I just dropped it down to about 150 by your hydraulic pump valve here. So I'm going to, and it's coming up to about 400 psi because of the temperature. That's the, oh, now I just did it too far. All right, that's maintaining. That's about 200 psi, something like that. So now I have 200 psi that is inside the cell. That prevents the cell from causing the fluid to turn to a vapor, to turn to a gaseous phase. So I'm going to leave things as they go now. Normally we would let it heat like this for 1 hour. The situation doesn't call for letting it heat for an hour, so I'm not going to stand here for an hour and let you watch that. We're just going to assume the hour is up. So assuming we're at our target temperature, during that hour you have to watch everything. You have to make sure that your back pressure doesn't increase. You have to make sure your primary pressure doesn't increase. If it does, you can bleed it off with your bleeder valve here on the hydraulic hand pump. And a lot of times this will increase as the temperature increases inside the cell. That temperature will cause your pressure to go up. And if it goes up a lot, then you will end up with hydraulic fluid actually coming back down into the pump. So we're just going to say that we've heated for an hour. We're ready to run our test. Everything is optimum conditions. So I'm going to now prime my hydraulic pump up to my target pressure, which is about 1,000 psi. I'm going to set my outlet ball valve. I'm going to open that to initiate filtration. I'm going to apply my target primary pressure here. Once I get to that, as fast as I can, I'm going to open this ball valve. As soon as I open this ball valve, since I got 100 psi coming into it, now I'm initiating filtration. I got 1,000 coming in here. I've got about 150 coming down. So I've got about an 850 psi differential pressure, and that's typically what you do with a permeability plugging tester. You're no longer constrained by the 500 psi differential. So I'm going to pressurize this up to about 1,000. Well, it immediately went up to 1,000. It's at about 1,100 actually. It's coming down just a little bit. Yeah, it's coming down slowly. All right, I'm going to leave it at that. The next thing I want to do is open my outlet ball valve, and now we are collecting filtrate. I set my timer to 30 minutes, and it doesn't hurt to have another timer to set to 7.5 minutes. So we'll just try to monitor that. And it's always a good idea after you first start collecting filtrate, you want to collect a little filtrate and see if you're see what type of filtration control you're getting. You may not have any filtration control. It's conceivable to fill up this back pressure receiver immediately. So what we do is okay, good, nothing. And you have to do that very carefully. What I did was I opened the outlet valve and to see what filtrate, if any, I collected. I didn't collect any. But you have to watch your gauge here too, because you can void your CO2 bulb by collecting filtrate here. So basically, that is the test procedure. Now what I would do is I want to watch my gauge. It's staying right above 1,000 psi. I want to watch this gauge, and after 7.5 minutes, I want to collect filtrate, and that would be my spurt loss. And then after 30 minutes, then I collect filtrate again. That will be my the final amount of the test, and I plug the amount of filtrate collected in 7.5 minutes, and I plug the amount of filtrate collected in 30 minutes, and that gives me my PPT value. Namely, we double the volume of filtrate. The API calls for 7.2 square inches of filtration area. We're using half of that. We're using a 2.5 inch diameter paper instead of 3.5 inch. So you have to double your filtrate volume. And the formula the API calls for, and different companies do it different ways, but the API formula is 2 times what you collect in 7.5 minutes minus what you collect in 30 minutes minus the 7.5 minutes. So that is the formula that you go by for your spurt loss, and for the PPT value, again, is 2 times whatever you collect in your graduate cylinder after the 30-minute test. So basically, that's it. This is the test. So this is the end of part 2 for the OFI PPT test. In part 3, we will shut this down. I'm going to go ahead and let it run for the full 30-minute duration. And then we will see what kind of filtrate, what kind of spurt loss we collect, what kind of filtrate we collect, and then we'll go into the cell breakdown procedure and the collection of data. So this is Larry Mitchell for OFI testing equipment for the PPT, PPA, whatever you want to call it. And this is the end of part 2 of 3 parts for the permeability plugging tester. Thank you for your attention.